Okay, Zoom, can you hear me okay? Okay, cool. Let me pull up my website. I haven't uploaded the worksheet yet. I'm just about to get to it. I've gotten a couple of answers in here, but on Zoom, did we do, let me pause this while I'm figuring out the recording. Okay, so in preparation for your quiz tomorrow, we're going to go over ionic, net ionic, complete ionic equations. So this is a problem that we had, I think, 1 or 2 worksheets ago. So first, I want you to write the formula for a reaction between hydrobromic acid and lithium hydroxide. What is the formula for hydrobromic acid? What is that? I can't stand this pen. I'm sorry. What's that gonna look like? HBr. So we're gonna have HBr plus lithium hydroxide. What's that gonna look like? LiOH. And what's it going to go to? First of all, what type of reaction is this? It's going to create water. So kind of, oh shoot. So we have, what is this? Acid. Sorry on Zoom, I'm up on the board, but. And this OH, what does this OH usually indicate? What type of compound? A base. So we have an acid-base reaction, right? So what are always the 2 products of an acid-base reaction? Salt and water, yes. So we're going to have water, H2O, plus, for this, I'm going to write HOH down here because y'all know I like that, and I know y'all don't, and I'm sorry. HOH, and what's our salt? Lithium bromide. Exactly. So this is just a chemical equation, okay? So now we need to get this into a complete ionic equation. Oh, shoot. Okay. Hydrobromic acid, soluble or insoluble in water? Soluble. This is going to be an aqueous solution. What about lithium hydroxide? Also aqueous, yep. Water. What's the state of matter? Liquid. And lithium bromide? Soluble, aqueous. I keep just putting Q instead of AQ. I'm so sorry. So, to do our complete ionic equation, we're going to separate all of the ions. So remember that aqueous means dissolved in water. It's just ions floating in water. And that's really what aqueous means. So for hydrobromic acid in water, an aqueous solution, you really have hydrogen ions and bromide ions just sort of floating around in water. And that's what that means. So if it's aqueous, you're splitting it up. If it's anything other than aqueous, leave it alone. So this is going to be complete ionic. We're going to have H plus aqueous plus Br minus aqueous plus Li plus aqueous plus OH minus aqueous goes to H2O liquid. We're not splitting this up into H and OH because it's not aqueous. It's just water. It's liquid. Plus Li plus aqueous plus Br minus aqueous. So that's our complete ionic, right? So what is a net ionic equation? Without the spectator ions, how are we going to determine what the spectator ions are? Yes, we're going to have to cancel out on both sides. I'm going to grab a different color pen. So we have a hydrogen ion here. Do we have a hydrogen ion on its own in our products? No, so that stays. Bromide ion. Do we have a bromide ion on its own down here? Yes, so we're going to cross those out. Lithium? Yes, so we're going to cross this out. And then hydroxide? No. So what this means is that our net ionic is just going to be everything that's left over. So everything we didn't cross out. H plus aqueous plus OH minus aqueous goes to H2O liquid. Does that help with the net ionic? Okay, cool. And then if this helps you remember, if you like hear this and you're like, oh my gosh, I'm not going to remember that, then don't remember it. Just forget it and do this. Just do this if you can't remember this part. But for an acid-base reaction, the net ionic equation is always hydrogen ion plus hydroxide ion goes to water. Always for acid-base. But if you look at an equation and you're like, I don't know if this is acid-base or not, don't waste your quiz time thinking about it. Just go ahead and do all the steps and get the answer that way. Okay. On Zoom, is there any topic that you're concerned may show up on the, I was about to say the exam, on the quiz that you feel a little unsure about that you want me to go over? I'll give like a couple minutes to type out anything you guys might have. I need water. So I'll go ahead and we'll do oxidation reduction, and then we'll do precipitation reactions as well. Okay, so redox reaction. Let me pull up an example question that we can go over. Also, if you just joined on Zoom, if you've already done this, you don't have to. If you're not sure, you can enter it again, and I'll see if you already did, and I won't put you in twice. But that's the form. Click that link and go ahead and sign in for me, and so the office can do their stats. Okay. Redox. That was number 9. So let's go ahead, before we get into reduction and oxidation agents, let's just start with what is oxidation and what is reduction. So I want someone on Zoom. You can unmute yourself and talk. You can type it in the chat. What is oxidation?
Is it when it gains electrons?
Take that, but flip it.
So when it loses electrons.
Yeah, when it's gonna lose electrons.
But isn't something going up? So it loses electrons, but it's... I could be wrong. Never mind.
So since we're losing electrons, our charge is becoming more positive. So going from like a +1 to a +5, that's an oxidation. That means we've lost how many electrons? 4. It could also be a -3 to a -1. That's an oxidation. How many electrons did we lose? 2. So try not to let the signs confuse you. Just sort of like do the math. Yeah. Okay. And then, so what is reduction then? Gaining of electrons. So this means our charge becomes more negative. So you can go from a +3 to a -2. How many electrons have we gained here? 5. We could also go from a +7 to a +4. Okay, so now that we've sort of got those definitions out of the way, let me pull up a reaction I can use for this. Okay. Nope, wrong worksheet. So let's do the problem. We're going to have solid nickel plus 2 aqueous silver nitrate. Goes to 2 solid silver plus aqueous nickel nitrate. Okay. Okay, let's go ahead and jump into this. How are we going to figure out which element's been oxidized, which has been reduced? Yes, we're going to have to start assigning some oxidation numbers. What's the oxidation number of nickel solid? 0. This is its elemental form. I should probably write these in a different color so it doesn't get messy. 0. Okay, let's go into silver nitrate. Trying to decide how I want to go about this. Okay. So remember, I'm going to bring this down just so I can write it out a bit larger. So remember, this all has to equal to a charge of 0. This is a neutral, right? There's no charge there. So we're just going to go ahead and start with oxygen. Does that work with you guys? So oxygen, what's the oxidation number for oxygen? 2 minus times this 3, so we're going to get -6. And then silver, what's the oxidation number for silver? +1, right? Right? Someone have their periodic table so I can double check that. It's 1? Okay, cool. I just want to make sure I didn't just like pull that out of thin air. So we have a -6, we have a +5. We need to get to 0. So what does nitrogen have to be? +5. You could also set this up like an algebra equation if that helps you more. So we have 1 plus x minus 6 equals 0. You add 6 over here, you get 1 plus x. Take away 1, you get x equals 5, right? If you work that out algebraically. Okay. What's the oxidation number of silver? Solid, elemental state. 0. So now we're going to go into nickel nitrate. NiNO3, 2. And it needs to come out to 0. So oxidation number for oxygen? -2 times 3 is 6, and then we have 2 of those, so it's times 12, right? Or it's times 12. It is -12. Wait, no. It's times 12. Am I saying that right? It is 12. Thanks. Okay. And then nickel. +2? Sorry, I'm going to have to look at a periodic table. Let me see, because I need to figure out if we need to go for the nitrogen or for the nickel. Okay, let me pull this up real quick so I can remember what I put on my key because I don't have my key up. Oh. It's the one worksheet that I didn't save a key for. So we're going to figure this out together, guys. It'll be okay. So nickel can vary by 1 or 2. Or it can be 2 or 3, right? And then on Zoom, where I'm getting that from is on your periodic table. Let me see if I can fish one out. They're tiny, tiny little numbers. And, oh my goodness. They're tiny little numbers in the little boxes on the periodic table. You know what? Can I borrow yours real quick? Just to put on the overhead. Thank you. Okay. So, do you see? Oh, shoot. These little numbers right here, that's a 3. There's like a 4 and a 5, maybe. So if we go over to nickel, nickel can have an oxidation number of 2 or 3. That's what those numbers are, the possible oxidation numbers. So the reason we always calculate for nitrogen, if you look over here, it can have several, right? Even though we put this -3 up there at the very beginning of the semester, these are all the possible oxidation numbers. That's why they always have you calculate nitrogen. I know that may have been confusing before because you're like, oh, well, it should be -3 because that's what we said. But we lied in the very beginning of the semester, and I'm really sorry about that. So here's where I want to go with this. This is just a little bit of a different thinking route than continuing to do the algebra. So nickel can either be 2 or 3, right? Let me return this periodic table. Thank you. Okay. So nickel can be either, oh shoot. What did I do with my pen? I'm sorry. I can't keep track of anything. So it can be 2 or 3. We don't really know. But my question, looking at this entire equation, looking at all the oxidation numbers we've calculated so far, do we really have to know exactly which one it is? No. Why not? It's going from 0 to either a +2 or +3. It doesn't matter which one of those we choose, whether it is 2 or 3, it's still being either what? Oxidized or reduced. It's still being oxidized. We're going from 0 to a positive number, right? So we're losing electrons. Our charge is becoming more positive. So does that make sense? I'm sorry that took such a weird turn. I wasn't anticipating it, but you know, should you come across something like this, check out those oxidation numbers. See how they compare to what you had in the reactant stage. Okay. So we said nickel is oxidized, right? Sure. Okay, here's where math happens. So she asked, why isn't nitrogen being oxidized? Which is a fair question because we're going from a +5, and to make this work, either one of these numbers, it would have to be above 5, right? The answer lies in this too. Because when we calculate that number and is greater than 5, so this oxidation number would have to be 2. And I just know that because of math. You don't have to be able to do that. So it'd have to be 2. We'd get this +10, right? Well, that's greater than +5. But we have this 2. This +10 is calculating the number for 2 nitrogens. Do you guys see what I'm saying? So it becomes +5 because you have to divide it by that 2 to get to 1 oxygen, or 1 nitrogen, I'm sorry. Does that make sense? Zoom people, are you okay? Does this make sense? I expected that to work out much more cleanly than it did. So nickel is oxidized. What's reduced? Silver is reduced. Okay, so which one is the oxidizing agent? Silver is the oxidizing agent. Whenever you're talking agents, you're just going to flip them. So the like sciencey explanation behind this is silver is being reduced. It's gaining electrons. It's taking electrons away from something else, which allows whatever it's taking electrons from to become oxidized. So it's the oxidizing agent. It's what's allowing the oxidation to occur. So which one is the reduction agent? Nickel. Because it's losing electrons, it's giving them up, it's giving them to something so that it can pick up electrons and become reduced. Would you guys like to go over another one of these redox reactions that I know will work out great and not
Yes,
have the
please.
periodic table mess that I accidentally sprung on you
Please.
guys? Did someone on Zoom say something?
I said, please.
Okay, yes.
Thank you.
I'm so sorry that happened. Oh, there's that announcement. Okay. So this equation is not going to be weird. I promise. I pinky promise. I shouldn't say that because now I'm going to work it out and it's going to be weird. But we've done this. SO3 2 minus aqueous plus MnO4 minus aqueous goes to SO4 2 minus aqueous plus Mn2 plus aqueous. So I'm going to give you a hint here, because if you look at this, you're gonna notice that the oxygens aren't balanced. But the reality is that we don't care for calculating oxidation numbers. You can totally ignore coefficients for calculating oxidation numbers. The only numbers that matter are those subscripts. So we're not going to go into balancing. It doesn't matter for this question. So the question is which element is reduced and which is oxidized, followed by which is the reduction agent, which is the oxidizing agent. So we're just going to start over here at the beginning. So we need to end up with a -2. What's the oxidation number for oxygen? -2, and we have 3. So we're going to have a -6. So we have x minus 6 equals -2. You're going to add that 6. And what are you going to get? +4. So sulfur has an oxidation number of +4. What would be the overall number for oxygen here? O4? -8. And we're looking for this. So we have x minus 8 equals -1. We're going to add 8, add 8. And x is equal to what? +7. Moving on to the sulfate. What's the overall for O4? -8. And here we have x minus 8 equals -2. We're going to add 8. And what's our x going to be? +6. Oh, excuse me. And then Mn2 plus. What's the oxidation number? +2, just because it gives you that charge. If it says like something like O2 minus, then it would be 2 minus. So like whenever you have a free element on its own, so this is just one element, and it has a charge with it, that's your oxidation number. Okay. Where did sulfur start and what number did it end up at? So it went from a +4 to a +6. Did it gain or lose electrons? Lost. It lost electrons. So was it oxidized or reduced? Oxidized. So oxygen, it gets a little funky, right? Just because we have 2 oxygens on this side. So this is different, but this is the same. So we're just gonna keep on moving. Okay, are you guys okay with that? Mn, what do we start at and what do we end at? 7 to 2. So did it gain or lose electrons? Gained electrons, so it was reduced. And that one is manganese. So the explanation for the oxygen, it all comes down to these subscripts. -6 divided by 3 is -2. -8 divided by 4 is -2. -8 divided by 4 is -2. So once you do that math to get it for a single oxygen, those numbers are all the same. So that's why that one is not oxidized or reduced. Does that make sense?
Instead of there being like 2 separate oxygens on that side, if there was one, would we still like say if it's oxidized or reduced? Or will it always just not be?
I don't want to say that it won't be a question just because sometimes chemistry teachers make things up that like don't happen in real life just for the sake of a question to see if you know how to work it out. But whenever you see something like that, whenever you see something, so even if it was just the sulfur, I want you to check and make sure there's no subscript right after that element. Because if there is, that means you need to do math to determine what the real oxidation number is. Yeah. If there's no subscript directly after that element, you're good. No math needed. So, which element is the oxidizing agent? Manganese. So that means that this is the reduction agent. Okay, I know we kind of stumbled through that first one, but Marley, did that help you out, this one?
Yes, it did.
Okay, awesome. Does anyone have any other questions over redox before we move on to precipitation? Uh-huh.
Like strong acids and stuff. I get kind of confused between like what would happen if like a strong acid reacts with like a weak base. You know? Does that make any sense? 'Cause
Yes.
I have had a lot of questions about that.
Okay.
in homework, and I was like, I don't know like what happens. There's like, I don't know.
I will tackle that question at the end because we have to do that session. Because I'm gonna have to do some searching for that one. Acid base is very like Chem 2. And I'm gonna apply for Chem 1 for a reason. Okay. So moving on to precipitation reactions. So precipitation reactions are all about your solubility rules, right? So let me pull up something that we can work through. So what exactly is about precipitation reactions? Just like identifying one or like stoichiometry or what are you guys needing help with? Yes. Okay, I will tackle that question before we move on. No, you're totally good. You're good. Uh, okay, this isn't much of a color difference. I'm going from pink or red to pink, but hopefully it's enough still. So let's take, right. So I'm going to tackle these oxygens. So I'm just going to write out the compounds with oxygen in them. So 3, 2 minus, that's -6. Or actually, I'm just going to write out the charges for the oxygen. Okay, so sort of going back to this, I'll tackle this a bit more like not just being like, oh, hey, here's why. Okay, bye. Have fun with that. So we're going from a -6 to a -8 over here, and that's a totally valid question. This is something that honestly, it took me a little bit to figure out. So like, I get it. I totally get it. So what's going on here is, so remember we calculated all these on our own. So I would ask like, what's the oxidation number for oxygen? So -2, and then we times it by 4, and that's how we got this -8, right? But so -8 is the overall charge for 4 oxygens. In the same way that for -6 is the overall charge for 3 oxygens. But we want to get it down when we're comparing oxidation numbers, we want to get it down to just one of the element, right? So that means we would have to take whatever that oxidation number or the overall charge that we've written down and divide it by the subscript. So the -6 divided by 3 is going to be a -2. -8 divided by 4, -2. And again, -8 divided by 4 is -2. Does that make more sense? Okay, cool. I hope that seeing it right now like that, maybe someone out in Zoom land sort of looked at it with a question mark and was like, I don't want to say anything. So hopefully this was a learning experience for us all. Okay, so precipitation. What is a precipitation reaction? Okay, wait, let's start with this. What is a precipitate? An insoluble salt. So insoluble insoluble salt. So if you put something that's insoluble in water and you dump it into water, what's going to happen? Yeah, it's just going to stay solid. It's just going to float around. It'll eventually settle to the bottom. I want to think of how to describe this. Okay. So a precipitation reaction. Remember, in a reaction, we're forming something, right? We're reacting two things together to make something new. So a precipitate is going to be on the product side. Precipitation reaction means we're making a precipitate, right? So all a precipitate reaction means is you're putting an aqueous, something aqueous plus something aqueous goes to something aqueous plus something solid. So if you see all aqueous on the reaction side and a solid on the product side, that means you've got a precipitation reaction on your hands. And the only way to determine this, to determine if something is, I'm so sorry, I'm talking way too fast. The only way to determine if something is a precipitate is to know your solubility rules. I don't really have a trick for them. It's sort of just a thing you need to memorize. I do have, I do have a Quizlet. It's linked on my website, and I have the solubility rules and then solubility practice, where I have a compound and you work on like recalling those rules and then determining if it's soluble or insoluble, and then that's the other side of the flashcard. So are there any other questions over precipitation reaction? No? Is there anything else that anyone on here is like, oh my goodness, this is in chapter 4, it might be on my quiz. I need some more clarification. Reaction yield, like, what do you mean?
There's like, I haven't done it on like homework yet, but like, I'm assuming there's like ways of reaction. I think it percent.
Like limiting reactant?
Yeah, I guess.
Is that what you want to go over? Because if you do, that's fine, I'll do it. I just want to make sure that that's what you're wanting.
No, I was just like, she's like, hold on, homework for like, homework topics. Yeah, because we did it last session.
Yes. Yes.
Now we did all of the story.
Yeah. So do you guys want to go over stoichiometry? Do a stoichiometry problem before we break? Okay, cool. Because all that we've gone over so far is sort of like the outlying parts of chapter 4. Stoichiometry is the big thing that is never ever, you're never going to escape it. Doesn't matter what level of chemistry you get to, it's just never going away. So I'll do a limiting reactant problem just because that involves stoichiometry and all that. So let me pull one up. Oh, you know what? Do you guys want to do, how do you guys feel about stoichiometry with molarity and trying to find moles and all that? How do you guys feel about that? Okay, you want to go over that? Okay. So the question, a titration of 45.00 milliliters of 0.865 molar hydroiodic acid and 0.700 molar sodium hydroxide occurs to neutralization. How many milliliters of base is needed? So I'm going to write out the information. So we have HI. Hi, that's hydroiodic acid. In the question, I give you 0.865 molar, and I give you 45.00 milliliters. And our base is sodium hydroxide. Honestly, this is probably like the most common base that you'll work with in lab, which is kind of lame because it's a weird base. And I don't, but I have to talk to her tomorrow anyway, and like to prepare for the test prep. So she was asking about like writing out how to show your work so you don't get partial points taken off. So I have to talk to her tomorrow. I'm like required to communicate, obviously. It's for my job. So, and I'm going to ask her about what I need to include in my test prep and whatnot. So I'll bring that up and make sure that I give you guys the right information so that you don't get partial points taken off and then you're like, the SI told me to do it and then I'm in trouble with her. Okay. So my question is we're looking for X, how many milliliters of base is needed? What's the first thing that we have to do? What do you have to do stoichiometry? That's for molar. But yes, we do need liters. Was that you or was that you? Okay, I can't tell with the mask. We're going to have to get to liters for sure. Yes, we're going to have a balanced equation. We can't go anywhere without a balanced. I mean, we can get to moles of hydroiodic acid, but I always just start with the balanced equation because you're gonna have to do it anyway. So we're doing HI plus NaOH goes to, what are we gonna form? Salt. What's our salt? Sodium iodide. And what else are we gonna form? Water. Is this a balanced equation? Yes. So what's step 2? This is step 1, write your balanced equation. What's step 2? What was that? Not for this one. This one, I decided to skip over limiting reactant. It'll ask you, so she asked, how will you know that you have to find a limiting reactant? How do you know when you need to find one? How do you know when you don't? So 2 things, or I guess 3 things. The question will ask you, which is the limiting reactant? The question will ask you which reactant is in excess. So if it's in excess, it's the one that's not the limiting reactant. And the other question is, it'll give you grams of 2 reactants, grams or moles of 2 reactants, and it'll ask you how much product is formed. You got that? Do I need to repeat that? Does that make sense? Okay.
So in a sense, with excess zinc, zinc is not a limiting reactant?
Correct. So she asked, like, if the question is like this much of whatever reacts with excess zinc, then zinc is what's in excess, and you don't have to worry about how much is present because there's plenty. Okay, so just looking at our given information, what can we find right now? We can find moles of hydroiodic acid. What is the formula that we're going to use? Molarity equals moles over liters. So for hydroiodic acid, our molarity is 0.865 molar. We're looking for moles. And how many liters do we have? 0.04500. Keep track of those sig figs. And then you're going to put this into your calculator. How many moles do you get? Actually, I probably should have done this along with. Three, 8, 9. Yes. Because sig figs, 3 sig figs here, 3 sig figs here. There's 4 here, but since we're doing since we're doing division, we go with the least amount. Least amount is 3, so it's 3. And that is moles hydroiodic acid. So step 3 is dimensional analysis. We're going to start off with the moles that we just found. What's going to go on bottom here? Moles of what? Yes. How many moles? 1. Where does the 1 come from? The coefficients. No coefficient means an understood 1. What's going to go on top? So, moles of what? NaOH. So if you get to a step like this and you're like, oh my God, I don't know what I'm trying to get into, think about the question. What's the question asking? What are we looking for? Milliliters of NaOH. We're looking for something related to NaOH. And this equation here is giving us that relationship that we can use. And then we calculate because we need to get moles. We have molar, we're trying to find we have molarity, we're trying to find milliliters. So that means we have to have moles to be able to calculate, right? So this just means how many moles of NaOH do we have? And finally, step 4. What's step 4? Yes, we're going to go back to that molarity equation. We have the molar. It was given to us in the problem. We have the number of moles. And we're looking for the number of liters, right? Because that's what our equation is looking for. How many liters? Yes, 0.0556 liters. What's the question asking for? Milliliters. How many milliliters is this going to be? Right. 55.6. Oh, sorry. Does everyone feel a little more comfy about the quiz? Okay, anyone on Zoom, any last minute questions? No? Okay, I will see you guys in class tomorrow. Good luck on your quiz.